Hi Srikkanth, you can start now.
Okay. Yeah. Hi guys. Now we're going to discuss the solution to uh, compress all segments. Uh, One of the harder problems in today's long challenge. Uh, yeah. So let's directly get to the problem statement. So we're given an array, okay, and we have to find, and we are given a function f on an array A. Let's call this an array B. Okay. A function f defined on an array B to be the minimum number of operations. Minimum number of operations uh, to make the array B size 1. So initially you have, so what are these kind of operations? So in one operation, what you are allowed to do is you're allowed to take any two integers a comma b and remove both these integers from the array b and add g of a comma. G is another function which I will define. G of a comma b is the highest power of 2 highest power of 2 in ax or b. So let's say a is 5, or in base 2 it's also 1, and b is 3. Then the highest set bit in ax or b will be the highest power of 2 in ax or b will be 4, because ax or b is 6, and the highest power of 2 that's less than 6 is 4. Or just consider the most significant bit and remove all the others. So this is a weird function g that is defined on two integers, and what you have to do, we're given a function f of b, which is the minimum number of operations that you have to make on array b, and each operation is take two numbers, remove them, find g of a comma b, and add it back to b. So let me just give another example so we can understand. Okay. So suppose we have an array b to be, say, 5, 6. So in one operation, we can take two elements. There are only two elements, so we take 5 and 6. So and then find g of 5, 6, which is g of 5, 6 is 2, and in one operation we can convert b to 2, and that's size 1. So we applied one operation. So f of b is 1. And of course, f of this array is 0 and so on. So as you can see, like there are in numerous, there are lots of ways to get. In each operation, you remove the numbers at once. So the size decreases by 1 each time, but you are free to choose any two integers. So, for example, for the array 3 to 1, there are lots of ways by which you could convert this to a single element array. So you could choose 3, 2 in the first operation. You can choose 2, 1 in the first operation. You can choose 1, 3 in the first operation, etc. So you keep applying these operations, and the order in which you apply them determines the last value that remains. So here in this case, the value that remains is 2. Kind of made a mistake here, I guess. Yeah, it's not the minimum number of hops. Like the number of hops always n minus 1. It's the minimum number that remains after all hops. So yeah, you're given an array B, and each time you choose two integers, you can choose any two integers you want, and you want to minimize the number that's there in the end. You do n minus 1 operations, and in each operation you delete two numbers, and there's this weird function g, and you add g of a comma b to it, and you keep repeating this operation until the size of b is 1, and you want to find the smallest possible number that can remain. And obviously, this number depends on the order and the choice that you made in your previous the n minus 1 operations. So first off, let me describe the brute force. So the brute, let's write the pseudocode for f, f of array b. So this is just a rough pseudocode that I just want to write to establish what the complexity of brute force is. Okay, so take for every pair, a comma b. So we delete a comma b, then we insert g of a comma b, and let's call this b dash. Dash is g of a comma b union b, and then we evaluate. So what's the answer? So this is one possible choice, and your answer would be minimum of answer f of b dash. So recursively we compute this. Actually, its the answer is infinity. And in the base case is of course if b dot size is 1, then return b of 0. Yeah. So this is the pseudocode to find f, and as you can all obviously guess, like this is a very expensive function. The time complexity is something like say t of n is the time complexity for f. We can find the recursive relation for t of n is n squared. There are n squared choices to delete a comma b, and what that results in once you've deleted 2 and added 1, you have an array of size minus 1 for which you need to find f again. So t of n is n squared times t of n minus 1. So yeah, if you expand this, you can get given is this big exponential squared, given minus 2, so on. So you get this is n factorial squared, which is pretty bad. You can't even pass the course of class, I think. So this is very expensive. Maybe with some uh, optimizations here, you can somehow pass the first task. But yeah, this is just to calculate f. The actual problem is we need to find sum of from AL for every subarray. We need to find f and we need to add them up. So let's say n. So yeah, obviously the task is we need to simplify f. Okay, we cannot rely on the brute force uh, expansion to find f for all subarrays because that's too expensive. It was n factorial square. So in problems like this, and as you can see, f is not a trivial function, right? F is some weird, it's a weird complicated function. But in most problems like this, what kind of happens is that the f turns out to be a very simple function. And so if we play around with the brute force a bit, we can get some conjectures, or we can get some idea of what f might be for a given array. And let's we can also manually play with some examples. And if you do that for some time, you can easily get the following observation, which helps you solve the problem, which is consider the highest set bit among all values in B. Okay. So let's say a B is one subarray, and we want to find f of B. So consider the highest set bit of all the values that are in B. Okay, so you can have something like 5, 6, 9. So in this case, the highest set bit is 3, uh, which is there in 9, 2 power 3. The third bit is set in 9, which is the highest among all the values. So let's consider this bit and what happens to values that have this bit. Okay. So in one operation, what you're allowed to do is you take a comma b, you take the highest set bit in A XOR B, and that is basically your g of A comma b is the 2 power k, where k is the highest set bit in A XOR B. So if the highest set bit is let's say j, or let's call it p. If the highest set is p, if the highest set bit amongst all the values inside p is p, let's consider a couple of cases. Let's consider a case both a and b have p. If both a and b have p, then what happens is g of a comma b will not have 2 power p, because a XOR b will not contain the beat bit, because the beat bit will be set in both a and b, and a XOR b will vanish, and this will be something less than 2 power p in that case. So let me enumerate everything quickly. So we have for case 1, a and b both contain P, or P bit is set. What this means is, so remember that P is the highest set bit amongst all the values in P, and we're considering two values, the two values that we remove in the first operation. If both have the P bit set, then we remove two numbers with P bit set, and we insert a number G of A comma B, which doesn't have the P bit set. So essentially, we are removing two numbers. What this operation does is removes two numbers with P bit set. Okay, and let's consider the second. Okay, so obviously the second case is only one of A comma B contain P. In this case, what happens is you're removing both A and B, and you're inserting 2 power B, because A, let's say one of A comma B contains 2 power B, the other doesn't contain. So A XOR B will contain will contain the P bit set, and 2 power B will be the highest because P was the highest set bit among all the values we defined. So so in this case, we removed A and B. One of them contained the P bit set, and we added A XOR B, which contained the P, which had the P bit set. So essentially, what we did is we remove one number which had P bit set, and we're adding a number which had P bit set. So essentially, the count of the numbers with the P bit set remains same. Here the count decreases by 2. Here the count remains the same. And the third case also the count remains the same. If neither A comma B contains the P bit set, then obviously nothing happens to A XOR B. G of A XOR B also won't contain the P bit, and the number of numbers that contain the P bit set will either decrease by 2 in this case, or in this and the third trivial case where both don't contain, they don't change. So the number either reduces by 2 or doesn't change at all. So the parity is constant. So if there were even number of numbers with the P bit set in the beginning, there will be even number of numbers with the P bit set at the end. And if there were odd number of numbers with the P bit set at the beginning, there will be odd number of numbers with the P bit set in the end. Okay. So that tells us that so that tells us two things. Okay. So if the number of numbers with P bit set was odd initially, then it will be odd at the end as well. So in this case, f of p will be at least 2 power p. In this case, if the number of numbers with the P bit set was odd initially, where p was the highest bit set among the numbers. Then if it was even, then we can't say anything. So it's greater than or equal to 0 in the even case, but in the odd case, it's very interesting that it must be at least 2 power p. So this is like a non-trivial thing that we have found out. Now let's see if we can get this minimum minimum value. We've proven that in this case the minimum value must be 2 power p, and in this case the minimum value must be 0. If we can obtain the minimum value in these two cases, then we've obtained a very significant simplification of the function b, which will then help us to calculate the summation earlier. So let's play around with the function g. So up to now we've not really we just considered g as a black box, like g could have been anything. But no, actually we used it to prove that to prove some crucial traits, but we didn't really apply g to some numbers. But now let's try to use g to make. Now we have a target, right? Depending on the parity of the number of numbers in the bit set, we have either 2 power p or 0 that we will aim to get using the operations in g. Okay, so let's consider at this point. Let's go through some examples, and let's do the first case, the odd case. Okay, here our goal is 2 power p. That's the minimum that we can do. So we have at least, so odd meaning we have at least one. So we have one number with a 2 power p bit set, and at least one. And then here we have some number of numbers, some which don't have the p bit set, and some which do have the p bit set. So let's take one number which has the p bit set separately. It can be any number we like if there are more than one number. And let's consider the other numbers. Amongst the other, there will be an even number of them with the p bit set, and then there will be an even number of them. There'll be some other numbers which don't have the p bit set. But because the sum must be odd, if we remove one, the number of numbers remaining must be even, right? And here, what we observe is if we take one of these numbers and apply g with these two numbers, what we will get is we will get 2 power p. So we will remove both of these numbers, and the g of ax or b will obviously be 2 power p. So if there existed a number like this, which didn't contain the bth bit, we can merge it with this number and convert, remove these two and add 2 power p instead. So we have 2 power p in the array, which is good because our goal in the end is to have only 2 power p remaining. And now what to do with the other. So remember, there were even number of these numbers. So we can pair these up. And in each pair, we apply g again. So g of 1. So 1, by what I mean is I don't care what these digits are. They could be 1 or 0. With another number, another similar number, will not have the p bit set. And these can be some other. So this will be a power of 2, but I'm not really sure which one. But the p bit is 0. Okay. It's interesting that if there are even number of numbers here, we can pair them up, and we can remove the p bit in all of the numbers here by pairing them up and applying the operation. So yeah, so once we've done that, what we will have is we will have 2 power p, because we will have 2 power p and some numbers which don't have the p bit set, and we can just absorb them with 2 power p. Right? If we do g of these two, we will get 2 power p. So remove both and adding this means just removing this one. So by doing this construction, all we need is we need at least one. We need at least one number which doesn't have the p bit set. If that happens, then we can easily obtain 2 power p. When will that happen? Even if we don't have one like so, we can merge two even numbers and get that. So if you have at least 3 numbers, so if we have at least three other numbers, we can do this. The reason being, so the number of numbers with bit set is odd. So if we have one number here, we will have either 0 or 2 or 4 extra such numbers apart from this guy. And if we have at least 3 other numbers, we can find either 2 even numbers, combine them and get a number with 0 the bit, or we already have a number with 0 the bit, which we can combine here, and we remove all all the other numbers which had bit set here because they were even, and we could pair them. So if there are at least 4 numbers, if the size of b is at least 4 and it's odd, then we can get our goal, 2 power p. So just to reiterate, f of p equals 2 power p if size of b is greater than or equal to 4, and number of numbers with bit set is odd. We can obtain similar construction for even numbers. If the number of numbers with bit set is even, in that case, what we will have is we can play around similarly. We can make it all 0. How to do that is take any 2. I should write x here. So take any 2. Let's fix them up, and our goal will be to convert these 2 numbers to 2 power p. Okay, so let's say we had 3 other numbers like the previous example. If we had at least 3 other numbers, we can convert, we can obtain 2 numbers with bit as 0. We can obtain 2 other numbers with bit as 0, and then with those 2 numbers, we can make this guy 2 power p. We can make this guy also 2 power p. Then we will combine these 2 and get 0. So, for example, suppose we had something like this. Okay, so here, let's fix these 2, combine these 2 to get p. We can combine these 2 to get p, and combine these 2 to get 0. Okay, so in this case, we need 3 other numbers apart from the 2 any 2 numbers that are the bit set. We can keep them separately, and we can merge all the other numbers with these 2 numbers to get 2 power p's. Then finally, we can merge them together to get 0. So it's 0 if p is at least 5, and this is even. Okay. So for subarrays of size at least 5, all we need to do is we need to find the frequency of the bit. Okay, I'll call it FRAQ. Frequency of the bit, and we find out if it is odd, then it will be 2 power p. If it is even, then it's 0. But this is only for subarrays of size at least 5 or at least 4. In each case, let's say at least 5. So if the subarray size is at least 5, we can do this construction, and we can f of b simplifies to either 2 power p or 0 according to whether the number of numbers with the bit set is odd or even. So considerable simplification there. So now we can obtain the summation trivial. All we have to do is maintain frequency of p for all p from 0 to 29, because 2 power 30 is the maximum value of 2 power 30 minus 1 is the maximum value of any number in the array. So so if we maintain the frequency table for every, if we can get the frequency table for the subarray, we can get f trivially. So if frequency of p is odd, then it's 2 p, otherwise it's 0. So this is like a standard technique. We can iterate the subarrays by fixing the starting point, fix the starting point and iterate over the ending point, and keep maintain the update the frequency table as you move right. And you can get you can visit every subarray and get the frequency quickly, or alternatively you can maintain a prefix sum of the frequency of each bit, and you can get INO form. So let's call it prefix f of p. So if you want the frequency of the pth bit from L to R, you just do prefix of R minus prefix of L minus 1, and you can get the parity by modulo 2 or and 1. So yeah, we can just visit every subarray and you can get the function constant, right? What about sizes of subarrays with size less than 5? Well, this is a very small number. We can do brute force, and factorial squared is okay. 4 factorial is only 24, so 24 square is okay. So for this will amount to a small number, because the number of subarrays of size with size less than 5 will also be O of n. The n plus n minus 1 plus n minus 2 to n minus 3, I believe. Yeah, so there are not a lot of subarrays and cost is not a lot, so we can do brute force for subarrays of length less than 5. For subarrays, for other subarrays, we can visit every subarray and maintain a frequency table. But the time complexity of this would be n squared, which will get you 30 points. Right. So now the major task for us is to find all subarrays, or find the count of subarrays with odd number of p, odd number of p bit set guys quickly. So yeah, like note that there are only 30 bits. So what if we can get the answer for each bit separately instead of visiting all subarrays, calculating p and doing that? Let's fix the highest bit that is set, and suppose the highest bit that's set is 29. Okay, let's try fixing p. If p is 29, then consider those numbers that have the 29 bit set. Let's say there are at indices I1, 2, so on to ik. So now we want all subarrays that have odd number of these indices. Okay, so one candidate would be any subarray from 1 up to I2 minus 1. So any subarray that starts here and ends starts in this range, ends in this range and starts in this range is a valid candidate. So we can count all those subarrays in a single go instead of visiting them one by one. Okay, so I iterate through the indices from 1 to n. Okay, and at some indices, we have to find the number of subarrays that have odd number of these special indices, which contain the peak bit I1, I2, so on like that. So how to do that? So the frequency of p again. If we go to the prefix method, so the number of occurrences of p in this subarray would be the occurrences of p in this prefix minus the occurrences of p in this prefix. Okay? And I'm really only worried about the parity, whether it's odd or even. So if we fix the subarray to end at a location here, okay, and find the frequency, find the parity of the number of numbers with p bit set, let's call those special numbers. Okay, so find the number of special numbers in this prefix and find the parity, if it's odd or even. Okay, and let's maintain odd count to be the number of prefixes visited before, which had odd number of special numbers, and the number of numbers which have even number of special numbers. Okay, so if we want odd number of special numbers at the end, and currently we have odd number of special numbers, we should go for even count. So any subarray that had even number of special numbers in the prefix, we can subtract that prefix from this prefix. This corresponds to this subarray. Okay, so by maintaining even count and odd count of the prefixes visited so far, whenever we are at a prefix, we find out the number of valid subarrays that ended a prefix that ended that particular prefix, and we can count all those subarrays in a single go and in linear time in one pass over the array. We can find the number of subarrays that had odd number of bits set. Okay, this will include subarrays of size less than 5. Okay, in this case, what we will do is we will go over all subarrays of size less than 5, and we will subtract out the value that we add from this method then. So because we are not counting these subarrays, some we are going to go for the brute force method for these subarrays. But because there are only linear number of such subarrays, we can easily iterate through them in a single go. So that's not an issue. So in all of n, we found out for p equal to 29. Okay, but what about p equal to 28? Okay. If p equals 28, no number that belong to p equal to 29 should be in this subarray. Okay, so that. Okay, so let's assume we solved it for p equals to 29, and we found indices like so. Okay, and we had these subarrays here. Okay, so for p equal to 28, okay, no subarray must contain I1, I2, and so on like that. Okay, because if these are special indices that had p equal to 29, if these special indices are present for subarrays that I want p equals 28, then that's not correct, right? Because p is the highest bit set. So if you want to find those subarrays that where the highest bit set is 28, we must avoid those numbers that had highest bit set as 29. So these must not be present in any of our subarrays that we consider. So all the subarrays that we consider, they will not cross these indices. So they will be present in these places. Okay, so subarrays that uh, will be candidates for lower P's. Okay, for lower P's, they will be between the special indices that we found for P equal to 29. Okay, so here what we do is we can remove these numbers. Okay, and we can consider these subarrays as separate arrays and add the answer for each of them separately and uh, put them together. Okay, so we will remove those numbers that were special. First mark those numbers that are very special, remove them, and whatever remaining subarrays that you get, find the answer for them separately and add them. Okay. So what will be the time complexity of this method? Well, there are only uh, 28. So there are only 30 bits, and for each bit, you will be removing a lot of numbers in between. But even if you didn't remove any of them, worst case, you will be having O of n for each bit. Okay. And since there are p bits, this 30 can be written as log a. So in O of n log a, we can get the count. Right. So that's, yeah, this gets points. So the most difficult part of this problem was to simplify f. F was a weird and difficult function to obtain by brute force. But what we all we had to do is we had to work through a few cases, get some conjectures, the or get some properties that f must satisfy. Uh, the one that's hard to find is that if size of b is greater than or equal to 5, then f of b is 0. B is 0 or 2 bar. This was the major thing that you had to find. And once you find that, the rest is simple. We just have just rest is counting subarrays. Uh, and yeah, that helps you get 100 points in this problem. So it was, I would say, a medium to hard problem because this observation is not obvious, and there's no way to say that such a simplification will exist. You just have to try it out and find it out. But once you do, the problem becomes very simple. So as such, there are no prerequisites. All you have to know are prefix sums, maybe, and bit set and closure. So that is it. Thank you guys for listening. Good luck.